We want to look at some properties of the exponential family distribution. We have it written here in canonical form. It's e to the power y theta minus b of theta, both divided by a of phi plus c of y and phi, where theta is some kind of location parameter, phi is some kind of scale parameter, a, b and c are known functions. And we can very easily turn that into a likelihood function, a log likelihood function for theta, given y and phi. For a single observation, we're just going to take y theta minus b of theta divided by a of phi plus c of y and phi. That's for a single observation. If we want a likelihood for lots of observations, we just need to add a summation and apply the function across individual values of y. Let's keep things simple by just considering single observations, and one of the first things we want to do is to find the score equation. So we're going to take dl, take the log likelihood differentiated with respect to theta, and we're going to find this is y minus b prime of theta over a of phi, and the rest of this is additive and disappears. Now what's so interesting about this is we can take expectations of this score function, and we've seen earlier that the expectation of the score function is equal to 0. So if we take the expectation of y minus b prime of theta over a phi, we know this is equal to 0, and we can work with this and break up the parts of the expectation. So what are we going to do? We're going to say that the expectation of y over a of phi minus b prime of theta over a of phi is equal to 0. And of course we can ignore these terms, and with a little bit of rearranging, we're saying that the expected value of y is equal to b prime of theta. Let's quickly check this. We said for the Poisson that theta was equal to log lambda. We also said for the Poisson that b was equal to this function, and we know therefore that b prime is going to also be this function. So b prime of theta will be equal to exp of log lambda, which is lambda. So the expected value of y for a Poisson is equal to lambda, as we expect. Okay, we're going to try another method, and if I wrote that u was equal to y theta minus b of theta divided by a of phi plus c of theta and phi, you'll see that I can instead now write my exponential family function as f of y given theta phi is equal to exp of u. Now, for any valid PDF, we know if I integrated the density over its range, it would be equal to 1. And we also know if I took the differential of this with respect to theta, I would be having something that was set equal to the derivative of 1 with respect to theta, which is 0. Now, the interesting thing that applies here is whether and where it's appropriate to reverse the order of these operators. So if I instead integrate the differential of expu with respect to theta, I know that whatever this is equal to 0. And we can use the chain rule here, so we know that what I'm looking at is the integral of exp of u multiplied by the differential of u with respect to theta. And remember here, whenever we talk about u here, we're specifically talking about this kernel of the exponential family distribution. So, if I move this out the way, we're trying to find the integral of exp of u multiplied by du d theta. So if we first find du d theta, what I'm looking for is the integral of expu with respect to multiplied by du d theta. So what I'm trying to find is the differential of y theta minus b of theta divided by a of phi plus a constant that doesn't involve theta and won't be there once I've done the differentiation. So we're looking at something that is y minus b prime of theta divided by a of phi. So if I add this back to the original problem, I'm trying to find the integral of expu multiplied by y minus b prime of theta divided by a of phi, taking the integration with respect to dy. Now the first thing I'm going to do here is to work round, multiply out this expu. So I'm looking at the integral of y over a of phi multiplied by expu minus b prime of theta over a of phi multiplied by exp of u, and with integrating with respect to dy. Next thing I can do, quite simply, is to break this into two procedures. I'm integrating y over a of phi expu dy, and I'm subtracting the integral of b prime of theta over a of phi expu with respect to y. Now there's a few terms here that are constant with respect to the integration, so we can take them outside the integral signs. So we're looking here at 1 over a of phi multiplied by the integral of y exp of u dy, and we're subtracting from that b prime of theta over a of phi multiplied by the integral of exp u dy. And now we get to something that's really very simple to deal with. We can instantly recognise what's going on here is that I'm integrating a valid probability density function over the whole range of values of y, so we know that this is equal to 1. So I can quite simply write this b prime of theta over a of phi multiplied by 1. The second thing we can do is we can see here that I'm integrating y multiplied by the probability density function for y. And again, we can recognise that very simply. That's the first moment, that's the expected value of y. So I have here the expected value of y multiplied by 1 over a of phi. So I have the expected value of y over a of phi minus b prime of theta over a of phi, and we saw earlier that this equals 0. And we're now in the realms of quite simple algebra, and we can see that the expected value of y is equal to b prime of theta for whatever values of b and theta we're working with. Okay, so we're going to look now, and we're going to continue with the basic idea that wherever we write u, we actually mean to write y theta minus b of theta all over a of phi plus c of y and phi. And we're using that throughout. So, finding a second moment, well, we know we're going to need to take the second differential of the integral of our exponential family function, which is exp of u, and we know that that's going to be equal to 0. And as before, we believe we can reverse the order of the operators, so I can take the differential of the integral of the differential of expu, and we know how to do that already. So we can write the answer to this. We're trying to find the differential of the integral of expu multiplied by y minus b prime theta over a of phi, and we're taking the integration with respect to y. So, what's the next thing we need to do then this time is to differentiate this once more. And what we might notice is that we have, when we move the operator inside, makes it a little bit clearer, that we are differentiating exp of u multiplied by y minus b prime of theta over a of phi. And what we can notice here is that we're working with the product rule. d theta, u of theta, b of theta is equal to d u of theta with respect to theta multiplied by v plus u multiplied by dv d theta. And we can do some of this quite simply already. We're still taking the integral of whatever we find, but we're looking at the differential of u multiplied by v. So I need to find the differential of u. Well, we've done this before a few times. I'm looking at exp of u multiplied by the differential of u, and I then need to multiply this by v, and then we need to find u and multiply that by the differential of v. So I now need to differentiate y minus b prime of theta over a of phi, and this is going to give me b double prime of theta over a of phi. And we're doing this with respect to y, and just to be very clear, let's keep all of this in the same set of brackets. Now, we're going to do a little bit of tidying and rearranging and spotting things we've seen before. So, the first thing we have 1 over a phi multiplied by 1 over a phi. This is constant with respect to anything we're working with, so I can bring that outside any other operators I'm working with. So I have 1 over a of phi squared, and I am integrating here something quite interesting, because I'm integrating y minus b prime of theta, but we've already seen before that b prime of theta is the expected value of y, and again if we look, we have y minus b prime of theta multiplied by y minus b prime of theta, so this term is squared, and I'm multiplying that by exp of u, and we can break the integral apart because there's a minus sign there, and then from this I'm subtracting. Again, we have terms that are constant with respect to y, so I can bring those outside the integration operator. So I have b double prime of theta over a of phi, and I'm integrating, multiplying that by the integral of x u dy. So a little bit of rearranging, and I can now do some pattern spotting, because what I have here is the integral of a PDF with over its whole range, so this is equal to 1, and I have here an integral of y minus the expected value of y squared over multiplied by the PDF, and we have a word for that, and that's the variance of y. So what I've found is that the variance of y over a of phi squared minus b double prime of theta over a of phi is equal to 0. And this is now some fairly simple reorganizing, and we have shown that the variance of y is equal to a of phi multiplied by b double prime of theta. If we very quickly check that for the Poisson, we said for the Poisson that a of phi equals 1, and we said that b of something was exp, so I can differentiate this twice. I still have exp, and I want to find exp of theta, and we said that theta was equal to log lambda, so for the Poisson I'm trying to find 1 multiplied by exp of log lambda, which is lambda. So for the Poisson we've shown that the variance of y is equal to lambda, which is the result we would expect.